Welcome to this example on actually applying dot product in 3 dimensions and then trying to find the coordinate system. We're going to be doing kind of projections of a vector in this example. Now let's take a look here. So we have 2 parts, okay, in here. So first let's take a look at part A, where it says create 3 perpendicular vectors for a 3D coordinate system such that one of the vectors is collinear with 1, 1, 2, and we want to make all the vectors unit vectors. Okay, so if we want to have 3 perpendicular vectors and one of the vectors be collinear, now collinear, we can just take that vector, and we want unit vectors, so we can certainly divide by the magnitude and we'll get the unit vector itself. I'm going to do the following. So this is for part A. Let me call vector number 1, and this is going to be 1, 1, 2. Now the unit vector for this would be, so I'm going to call this one unit vector u1, would be the vector itself. So that would be, maybe let me just write it as v1, and it would be divided by the actual magnitude. And I'll find that in just a moment. Now, if I want a perpendicular vector to this, I can use the dot product, because I know that using the dot product, so between 2 vectors, if the dot product is 0, then the angle between those 2 vectors is 90 degrees, which makes them perpendicular. And that makes my life a lot simpler. Now, this vector is not very complicated, and it's 3 dimensions. So what I like to do is, if I'm going to create a second vector which is perpendicular to this, with the knowledge that the dot product between them must be 0, I like to zero off one of the actual components. I'm going to zero off the z component or the z component, so that if I do the dot product, so 2 times 0 is going to be 0. And then finding these 2 components, so finding the first component and the second component, is going to be rather simple in this case. So notice, if I was multiplying, so this 1, I can make this 1 as well. And then 1 times 1 is going to be 1. And then I can make this negative 1. And if you notice, if you take the dot product in between those 2, then it clearly is equal to 0 right there, because it's just the sum of the multiplication of each of the components. So if there are no other restrictions, we can definitely take this vector. Now, this is not unique. You could have chosen, another vector. You could have even zeroed off the x component of this one and then just simply worked with the y and the z component of vector number 2. So this is not unique. You can find many other vectors, okay, for this. And in fact, you can even take the opposite of this vector, and that's also going to work. I'm going to just stick with this one. And then, of course, if I wanted to know the unit vector here, so this is going to be the unit vector number 2, then that's going to be just v2 divided by the magnitude of v2 itself. So that would have been the unit vector for that. This one is easy in that case. Now, my third vector, this one's going to be a little bit more challenging. It would be easy to find an actual perpendicular vector to v2 directly, but we need to now find a third vector which is going to be perpendicular to both v1 and v2. So that means the dot product between them is going to have to be 0 throughout. So if I look at this, now let me just actually write out the components this time around. So here are my components that I want to be able to find, x, y, and z, for this one. And what I want is, I want v1 dotted with v3 to be equal to 0. And notice, if I do that dot product, it's going to be x plus y and then plus 2z. this is supposed to be equal to 0. Now, if I do the second one, so that's going to be v2 dotted with v3, that's also supposed to be 0. And this one is going to be actually much easier because the v2 z component is, or z component is 0. So this is going to be that, which from here, notice if you isolate, you can see that x is equal to y. And so that's going to be the choice that we will have. So x is going to be equal to y, and well, the easiest thing to do is just choose x is equal to 1, for example. And they don't give us any restrictions, so we can choose whatever we like. We can choose x is equal to 2, equal to 3, whatever it might be. But y is going to be the same. Why make this complicated? So just let x and y be equal to 1. So I'm going to be making both of these components 1. Now, if you make both of those components 1 and then you substitute back into here, then you can certainly solve for your z. And so that's going to be 1 plus 1 plus 2. Z is equal to 0. Well, this is nothing else, as you can see here, if you work this out. So 2, let me just move these things around in here. So divide by 2, and you're going to get -1. Okay, so there you go. So that's my third component. So this component is going to be, so v3 is equal to 1, 1, and -1. So that is it. And of course, if you want the unit vector, and this is going to be unit vector number 3, so though you need v3 divided by the magnitude of v3. Now, let's find all of these magnitudes. So first, finding the magnitude for v1. Well, if you recall, so finding the magnitude of anything is going to be just the components itself. So I'm going to actually do this here on the side. So that would have been the magnitude of v1 is going to be equal to the square root of 1 squared plus 1 squared plus 2 squared. And so this is going to be 6. So that's my v1 component. My v2 component, if I want the magnitude of that, this one's even easier because it is just 1 squared and 1 squared, which is going to be square root of 2. And then your v3 component, so your magnitude of that, well, that's just a bunch of 1s. So again, now notice it's -1, but it's squared, so it's going to be still 1. So this is going to be square root of 3. So now you found your actual unit vectors, so you can just substitute that back in there. So as a whole, you're going to have your u1 is equal to, so this is going to be 1, 1, 2 divided by, okay, square root of 6. Your u2 is going to be 1, -1, 0 all over square root of 2. And then your unit 3 is going to be 1, 1, -1 all over square root of 3. So there are your 3 vectors. Now, let me just actually graph them for you. So I'm going to use math3d.org to graph this. And you will see, at least visually, we want to be able to see if these are actually perpendicular. It's going to be a little bit tough and challenging to see that, but we're going to give it a try. So let me load math3d.org and be right back. All right, so here's math3d.org. I'm going to add the object. I'm going to add a vector in here. So this was 1, 1, 2. And this is divided by the square root of 6. So that's my one of the vectors. I'm going to add another vector. Here's the other one. And this one was 0. So 1, -1. And this thing is divided by 2. All right, so you can hopefully see ever so slightly. I mean, there we go from the top. So these are, perpendicular in some way. And let's make our third one. I'm going to add this one. The last one was 1, 1, and -1. And I'm just writing square root, and this is going to be 3. So there you go. So here's, so you can see here. So these are two perpendicular. This one is also, looks like, just depends on which angle you're looking at. If you look at it like this, it doesn't look so perpendicular. Of course, you have to be kind of mindful, all right, as you are glancing at these right here. Okay, so there you go from the top. That's tough to see here. So those are your 3 perpendicular vectors, all right? So here is kind of an upper view right here that you have. So this is pretty neat. You can try to put them in there and then see that. All right. Okay, so that is an actual visual viewpoint. Now, let me go back and let's answer part B. So for part B, what are the components? So now they give us an actual vector, and it's asking us for the components of this vector with respect to the unit vectors you created in part A. Now, so this is 3, -4, and 1. What we're used to, or what you are used to, so 3, -4, and 1. So if you go back to your regular unit vectors, which were basically I, okay, J, and K, and these ones were 1, 0, 0. This one was 0, 1, 0. So this is your standard definition of your unit vectors. Then it's very easy, right, to pick off the components. So you know that this is just 3 I, and this would have been, minus, I guess, because of the negative. So -4 or -4 J plus, and this would have been just K because it's 1. So that's very easy to be able to see that. Now, what we are doing is we're not using these as our coordinate system. We're using these as our coordinate system. So how do you get the component on each one? You have to use projections. So what we're going to have to do, so let me call this, vector, I guess I called the other ones V1, V2, V3. So let's call this just V, vector V. So what we want to be able to do is we want to be able to project the vector V on each of these components. So if this is my vector, then I am projecting first onto U1. Then that, this particular projection, right, of course, is going to be a vector of its own, but you're projecting onto U1. So the component of U1 is going to be that leading magnitude that we have in here. So this is something that we want to be able to find out and calculate. Now, the projections, so as you're working through, so this is something that you hopefully still remember. So the projection of a vector, so vector, now in this case V, onto, now in this case it's onto U1, is going to be equal to the dot product between these, right? So this is going to be the dot product between these, divided by the dot product, all right, of the vector you're projecting onto. And then this is, okay, in that particular direction. Now, this right here, this is just 1. So don't forget, well, this is just equal to the magnitude of U1, right? So this is what we would have right there. And this would have been squared. But the magnitude of this is equal to 1 because it's a unit vector. So this falls off in here. So we don't have this at all because it's just equal to 1. So really, we are just looking for this. That's what we want, and we want it in this particular, this direction, okay? So that is going to be the component. So that's not hard to do. So we have 3, -4, and 1 dotted with, now this is going to be dotted with the first one, so 1, 1, 2. And of course, this is divided by the square root of 6. So if you do that, this is going to be 3 minus 4 plus 2. And all over the square root of 6. So that's going to be 3 minus 4, -1. So that's 1 all over this. So that's my first component, right? So this is going to be that. And that's the component in the direction of this. So that's my first one. Now my second one, we're going to do the same thing. So for the second one, you need 3, -4, 1 dotted with. Second one was 1 minus 1, 0 all over square root of 2 in there. Well, the dot product in between those is going to be 3, and this is actually plus 4, and then 0, right, over square root of 2. So this is 7 over the square root of 2. And so this is going to be in this direction. So that's my second one. So here are the components. One, here's the component of the second one in that direction. And then finally, the last one, that's going to be 3, -4, 1, dotted with 1, 1, and this was -1, all over square root of 3. So you have that. So that's going to be equal to, I guess, 3 minus 4 and minus 1 all over this. So 3 minus 4 is -1, so this is -2 over this. So that's my last component, okay, within there. This is going to be U3. So here it is, okay? So here are all your components that you have with respect to your new coordinate system. So this is interesting because you do use other coordinate systems. When you're in high school and you're studying this for the first time, you are so used to having your coordinate system like this because that's what you've been taught all of these years, especially, you know, starting from X and Y, so in the plane, and then you move over to 3D, and this also, of course, makes sense. But it turns out that in real life, sometimes we use different unit vectors to create a coordinate system. And then we want to be able to sometimes translate from one coordinate system to another coordinate system. And if you go on into post-secondary and you start studying, this is a nice little short introduction to let you know that, hey, you can actually write out vectors in terms of other vectors. And that's why we use projections, right? So that we can actually take the components as well. You know, you have seen a projection before, and those projections were, for instance, in an example of doing forces, right? Or if you're calculating work, you know, you want to be able to see what is happening there. Okay, so that you certainly do use. So this is the example. You can certainly plot this vector in Math 3D just to try to see how it looks like. But I'll leave that with you if you want to be playing around with this. So that is it for this example. So that's how you would solve parts A and parts B. Thanks for watching and happy studying. Okay, we'll see you in a future video. Bye, everybody.